And based on the topics that were discussed throughout this session, it seems to me that there are two different topics that bear additional discussion here right now for a little bit of time. Perhaps this weird bump in the saturated size frequency distribution is a good topic to start off this discussion section, especially because there was some really good back and forth going on earlier, and if there's interest, I believe it would be beneficial to discuss now during this discussion section. So I'll open it up with that as a suggested first topic.
Yeah, I guess Stuart, this was, I guess, the back and forth we had about the sort of very subtle uptick in the somewhat steepening of the smallest end of the size distribution. That's my phone.
That's not me. Yeah, so while you're looking at that, you had attributed it to a potential real process, and I was suggesting that I see this in a lot of data regardless of what the pixel scale is. I see it usually as a function of the pixels. So once you get to smaller than, I've not seen it greater than 40. I've not seen it at 30.
Yeah, so that's why it was, it's ambiguous. And I Caleb and I have talked about it before because, Caleb is actually the one who did the counts, and it's subtle enough that it's not, it could be a, an artifact. And the only way to really tell would be, I guess, to actually purposely count, a terrain with like 10 meter and smaller craters on purpose that is in equilibrium, which almost nobody would do on purpose.
Well,
might be worth doing.
There was a paper that was recently out, and I remember it because I reviewed it. I have to remember what it was or who the authors were, but what they did was they actually took terrain and they purposely degraded it by like a factor of 5 and then by another factor of 5, and they did crater counts on it. And I'm pretty sure that they saw that effect, and it was not at any particular original pixel scale. So it wasn't at 5 meters, it was at 5 pixels. Yeah, I'm looking at it now. This is, I'm looking at my version as a reviewer. Wang et al. From Icarus. I know that's a common last name, so that probably doesn't help you. But it would have been a paper out probably, so my last review was October of 2019. So either at the end of last year or into this year, where they actually looked at it, and I can tell you the title. The title would be The Minimum Confidence Limit for Diameters in Crater Counts. And I think that trying to repeat that study or using theirs would be the way to tackle this, because that way you could see, is it really a real function of the terrain, or is it a function of this minimum diameter? Because we saw it a lot in that 2014 study, especially with the volunteers. As I mentioned in the chat, we had to throw out over half of the data from volunteers because it was right within that 18 to 25 pixels, but 18 was the minimum that they could identify, where there was just a huge hump, and we attributed it to this aliasing effect, where you just start to manually do slightly larger craters. Obviously not intentional. But I guess my point was I would just urge caution in interpreting that as a real feature until you could really verify that it isn't.
Right. No, I agree.
Does anyone else have any thoughts about this topic? I know that we were trying to unmute folks who had participated earlier, but scrolling through this list is long. Is there anybody who would like to contribute?
It's a highly technical topic.
Yeah, it is. I will just add that, I've been doing these kind of very detailed counts in the Apollo terrains down to 10 meters and, so well into saturation, but not below 10 meters. And I've been seeing kind of what you're talking about, but actually in some areas, like it even does even weirder things, like it kinks even farther from saturation one way or the other. And I've been trying to figure out what that means. So, and this is well above, resolution effect. So, except for the idea that as you're maybe as you guys were discussing, as you're getting closer to resolution, the diffusion may make it harder to see those craters. So it could be due to that. But yeah. Anyway, I was just saying I don't have an answer, but I'm also puzzled by this.
Well, the reason I suspect that there could be something going on, just sort of qualitatively, I don't know if people watch the Chang'e 4 landing is a really cool. There's this really cool video of the lander coming down, and you see the very much the fractal nature of the surface of the moon in these equilibrium terrains, where you're zooming in on the surface of the moon, and it's like the same pattern repeating. You're just growing this, this self-similar surface up until the very, very last minute when you start to see the texture of the surface, the rocks and the boulders and things. So there's a qualitative change in the surface once you get to the scale of like rocks and boulders, right? That sort of sub-meter scale. So there is a physical transition in the material that occurs around that scale. Now, whether that translates in some way to these crater counts, I'm not going to say till we do a really well characterized study. But there's another thing that I had a former undergrad student who did some work on crater rays, looking at measuring crater rays and trying to understand what sets the length of rays, and sort of looking at the interplay between the ejecta and this sort of space weathered skin on the surface. And there does seem to be a transition at these sort of tens of meter sized craters where the rays seem to get proportionally larger. And our hypothesis for that was that with the larger, when you get craters bigger than, tens of meters, 100 meters, the very distal ejecta is hitting at very high speed and making secondary craters and things. But you get to really small craters, that same, a few crater diameter away, the distal ejecta is going to be hitting at really low speeds. You're getting into this this non-hypervelocity. So you're just sort of putting material onto the surface rather than blasting it and making a crater. And it could be that if secondaries are what's kind of driving, and distal ejecta is driving a lot of the degradation process, there might be a change just from the hypervelocity to sort of gentle blanketing that's occurring for the distal ejecta at those small scales. But it's all speculative at this point.
Well, I think that was a good continuation of the discussion. And then since we ran a bit.
Clark wants to unmute.
Oh, Clark, yeah.
Yeah, he is unmuted.
Okay.
No, he's muted. He was.
Yeah, I guess hypervelocity is the wrong term, because they are going to be sub-hypervelocity, but there is you can still make a kind of a crater. If you throw a rock at the ground, you'll make a hole in the ground and disturb material. But to some level, you get small enough and slow enough, you just stuff just hits the ground and stays there. That's kind of what I'm getting at.
Okay, I was gonna talk to Dave Minton about what I wrote about, just after your talk about the Perlin noise.
Oh yeah.
From your answer, it sounded like you're trying to make things look as close to reality as possible, but it seems to me the real value of what you're doing is to identify the physical processes that actually lead to the appearance that we see. And so it would seem to me that there would really need to be something going on the moon in the cratering process, and maybe other processes that would would explain why it looks better when you add this Perlin noise.
Yeah, that's a fair point. But I'll say a lot of the things that we're looking at, for instance, like what sets the scallopiness of the rim, right? So I've been working on like a little rim finding algorithm that can pick out the sort of the shape of the rim, and then you can do like a Fourier series analysis and figure out what's the amplitude and wavelength of scallops. And then you do this at different size ranges, and you can see, well, how does the character of a scallop feature change with size, right? So, but that's entirely empirical, right? And we can mimic that without really knowing what it is that makes scallops the way they are. Now, what actually sets that is probably has to do with the rock mechanics and how landslides happen and failure of the rocks. I would say that what I would be doing would be to sort of parameterize the constraints. Like, what do the observations tell us? What, give yourself a number for, like, well, this feature changes by this amount across this scale. And then that serves as a constraint to some physical modeling for how this works. And I know things like, hydrocodes are not able to reproduce these kind of features. It has to be some sort of modification process that's happening at smaller scales, right? So
well, I'm guessing that as you pursue this work, you'll learn how landslides work on the moon a little better.
But what I'm after really is the question of are the Highlands craters in equilibrium? What does equilibrium look like for these kind of things? What are the important parameters? And I just want to, I guess, fake it till I make it, right? Fake the craters till I can know I could fool somebody like Stuart. I could hand him a fake terrain and he says, wow, that looks pretty good, which he hasn't done so far. So
yeah, actually, we need to repeat that 2014 study, and I keep emailing you and then forgetting to email you back once you respond.
Yeah, it's a lot of it is just trying to get a handle on the important processes, even on the simple craters, let alone. But I got some ideas. We should talk offline sometime about how to actually approach this in a more systematic way, because I would like your help with some of this.
Thank you.
Yeah, thanks, Clark.
Okay, there's a comment question in the chat from Michael. Oh shoot, Devious last name. Sorry for butchering that, Michael. That says, true that max impact velocity for a secondary cannot be greater than the escape velocity of the target body, ?
Yes, that's true. That's sort of a definition of secondaries. They are slower. Now there is this sort of intermediate population called the sesquinaries, which Kevin Zonley, I believe, was the one who coined that term. This is when you have a moon or a satellite, you can have ejecta that escapes. It's above the escape velocity of the moon, but lower than the escape velocity of the system. So it goes in orbit around the system and then re-impacts one of the bodies. So he was looking at this for the Jovian satellites, and I guess the Saturnian satellites is a process you care about, where you can have ejecta from one moon hits another moon. Same thing can happen on our moon. You can have ejecta that leaves the moon for a bit, goes in orbit around the Earth, and some small fraction of it will re-impact the moon. I had a student look at this to see if it was important for anything, and it's probably not. It's a very, very small fraction of ejecta becomes sesquinaries on our moon.
Great, thank you, David. So we do have a few more minutes before the afternoon session. I personally would like a little break to grab a snack before we do that. But I did want to solicit revisiting the source of binary craters discussion that we were having with Paul Wren's talk, because although we had some great discussion, we did have to cut that a little short. So Michelle, can you help unmute Paul and the others who would like to be particularly involved in this discussion? please let us know in the chat, and we can go from there if that's a topic that continues to interest people.
So I've unmuted Clark and Romina, who I think were part of the original discussion as well. And Paul's unmuted, and I think David was part of it as well, and he's already unmuted.
Yeah, my other foot is in the world of planetary dynamics. In fact, I'm sort of attending another dynamics conference simultaneously to this one. Bad idea. Don't learn from my mistake. But yeah, so a lot of my colleagues work in the dynamics world. So it's really interesting. I don't think there really is a full explanation for these populations, as Clark pointed out. There's pretty good statistics for binaries, and it's actually really hard to make the wide binaries you need to make these happen, because I believe it was Seth Jacobson, who's when he was working as a student with Dan Shears, was showing that when you make asteroid binaries through this fission process, when they get wide enough, they get stuck before they get too wide, because the tides are too weak to actually keep driving them apart. And then they're susceptible to getting disrupted and becoming pairs. So at the same time, it's actually really hard to find wide binaries. There's observational biases against finding them, especially for the really small ones. Actually, a question for the doublet craters is, what are the constraints on the size ratio between the impactors for those? They tend to be close to equal size?
You mean when we're looking at doublets on planetary surfaces mostly? Mm-hmm. I think that there's a definite bias toward bodies that are close to one another in mass, because I suspect that if you had a much smaller body, kind of like Ida and Dactyl, mm-hmm. The smaller impactor would get lost in the crater of the large one. That's just my hypothesis, but certainly we see them. They're not all the same size, but I suspect their masses are never more than like 100% increase from the small to the large. Mm-hmm.
Hi, hello. Do you hear me?
Hello.
Yes, we can.
Yes.
Well, I'm Romina Disisto. I ask about the binaries. Sorry, I am here. Well, no, I want to thank all the answers about the binaries, and I am from the dynamical astronomy part, so that's why I asked about this. And no, for me, I think that to think that those crater pairs are only from binaries is, like Dr. Chapman said, is a part of the problem, you know. I mean, binary asteroids are separated in space, and probably they produce craters separated in the target. Very few binary asteroids strike in the same place of the asteroids, I think.
Yeah, we were seeing in a lot of the papers when we were doing our lit review on this, that everyone's in agreement. There's statistically the orientation of the two bodies, even if you have widely separated asteroids, there's so many ways they could hit a planetary surface such that they're so close to one another in terms of where they hit that you would not get any evidence of a binary system in that case. So we're definitely only looking at constraining the very low end of what the actual binary population might look like.
Okay.
Well, Paul, you're looking at really rather small craters as binaries. I think a lot of the earlier ideas about doublet craters involved rather larger craters, you know, on Venus and so on. And there's just many, many more doublet craters than seem to be explained by what we know about double asteroids. So it's a real puzzle.
Yeah, and when I did my work on Ceres, the whole point was let's see if we can find evidence of small binary asteroids in the main belt that you can't currently detect with most instrumentation right now. But I had a chat last year with Stuart because he was asking about bigger impact. What about large doublets on Ceres? And I had filtered out those craters. So I went back to the hotel in Flagstaff and just did I was watching a Gilligan's Island or something and looking around. And I found an astoundingly large number, very surprising number of large binary, impacts, doublet craters. It's very surprising.